For over a century, Albert Einstein's theory of general relativity has been our map to the universe. And you know what? It has passed every single test we've ever thrown at it. But what if there's a tiny, almost invisible crack in that perfect facade? Today we're going to dig into a really fascinating test of gravity itself. And it all comes down to one simple but profound question. Think about that for a second. We just assume that gravity gives the same marching orders to everything. It tells a planet how to move in its orbit, and it tells a ray of starlight how to bend its path. But what if it doesn't? What if there are two slightly different rulebooks? Answering that question is what this is all about. You know, general relativity is probably one of the most successful theories in the history of science. But science isn't about just accepting things, right? It's about pushing them, testing their limits, trying to find where they break. And that's exactly what we're doing here. We're putting Einstein's universe to the ultimate test. So this is the core idea right here. According to Einstein, the gravitational pull that keeps Mercury in its orbit is the exact same force that bends light from a distant star as it passes by our sun. It's one force, one rulebook. No exceptions. This is a fundamental prediction, and it's something we can now measure with just mind-boggling precision. Okay, so how in the world do you measure if there's a difference between these two effects? Well, scientists have a name for it, and it's called gravitational slip. You can think of it like a super precise ruler that we can use to look for any tiny deviation from Einstein's theory. Let's break that down. Imagine gravity has two different voices. The first voice is talking to matter, to planets, asteroids, you and me, telling us how to move. The second voice is talking only to light, telling photons how to bend. Gravitational slip is simply a way to measure if those two voices are saying the exact same thing, or if they're slightly out of sync. And this right here is the dividing line. On one side, you've got general relativity. The two paths are identical, the two voices are in perfect harmony, so the slip is zero. Simple. But on the other side, you have all these other ideas, these modified gravity theories. And a lot of them predict that the paths can be different. That would mean the slip is not zero. So this one little number becomes a huge deal. It's how we can tell these cosmic models apart. So if the slip isn't zero, what could possibly be causing it? Well, one really interesting alternative idea comes from a framework called dynamic vacuum field theory, or DVFT for short. And it all starts with a pretty wild idea about what empty space actually is. We usually think of a vacuum as, well, nothing, just pure absolute emptiness. But DBFT says, hold on a second, what if the vacuum is actually a physical medium, something with its own properties that can react and respond when stuff moves through it? If that's true, it changes everything. So in this picture, gravity isn't just space and time getting warped. It's more like an effect that emerges from how this vacuum medium reacts to a massive object. And that means gravitational slip isn't just some random number, it's a real physical measurement of the vacuum's own properties. Now, what's really cool is that this theory turns the whole idea into something you can actually calculate. It says the vacuum has a certain response in the time dimension, we'll call that A, and a different response in the space dimensions, we'll call that B. The slip parameter, gamma, is just the ratio of B divided by A. It's a direct measurement of whether this vacuum medium reacts differently to space than it does to time. Okay, so we've got a theory and a way to measure it. Now comes the fun part. We've got to check the data. We're going to look at two totally different places in the cosmos, our own solar system and then way out among distant galaxies, to see if this idea actually holds water. We're going to start close to home. Right here in our own cosmic backyard, we can make unbelievably precise measurements of gravity. This is where general relativity has faced its toughest tests. And this is what DVFT predicts for the slip in our solar system. The number is about 10 to the minus 13. To give you an idea of how small that is, that's a decimal point followed by 12 zeros and then a 1. It's so close to zero, it's almost funny. The theory says that in a strong gravitational field like ours, the effect basically hides itself. And here's our best actual measurement, which came from the Cassini spacecraft that flew around Saturn. It found that any slip has to be smaller than about 2 times 10 to the minus 5. So let's connect the dots. The theory's prediction is about 100 million times smaller than what we're even capable of detecting. In other words, this theory passes our best local test with flying colors. Okay, so the theory works here at home. But what happens when we zoom way, way out? We can look at how light from a very distant galaxy gets bent around a closer one. It's called strong gravitational lensing. And it turns out, even out there, all the data points to a slip value that is incredibly close to 1. And this leads us to one of the biggest puzzles in all of astronomy. We see way more gravitational lensing around galaxies than their visible matter can account for. The leading explanation for years has been dark matter. Some other theories tried to explain it with a really big gravitational slip, but if our best data says the slip is tiny everywhere we look, well, what's going on? And this is where dynamic vacuum field theory comes in with a really clever answer. It has a way to explain all the observations without breaking any of the rules we just established. It's got a surprise up its sleeve. So here's the twist. DVFT says the answer isn't a big slip. No, instead, it introduces a completely different feature that only really kicks in over huge galactic distances. It's an extra bit of gravity called a logarithmic potential. All that means is its strength fades away much more slowly than normal gravity, so it only becomes a big deal on the scale of entire galaxies. Let's just walk through how slick this solution is. First, you keep that slip parameter super close to 1. That makes sure everything looks perfect in our solar system and agrees with the lensing data. Second, you add this new logarithmic term, which provides just the right amount of extra gravitational pull you need on those galactic scales. And what you get is a single theory that can explain the extra gravity around galaxies without messing up the precise physics of our own solar system. It just threads the needle perfectly. So, what's the big takeaway here? Well, if a theory like this is on the right track, it really forces us to completely rethink one of our most basic ideas about the universe, the idea of nothingness itself. All right, let's just recap the big points. We've seen that gravitational slip is this amazing tool for testing general relativity. We looked at a theory, DVFT, that predicts the slip is tiny everywhere, which lines up perfectly with what we see. And this theory explains that extragalactic gravity with a totally separate feature, that logarithmic potential. But the really profound idea, the one that sticks with you, is that empty space might not be empty at all, but an active, dynamic medium. And that kind of leaves us with this final amazing thought. For hundreds of years, we thought of empty space as just a boring, passive backdrop for all the action in the universe. But what if it's not? What if it's an active player in the game? It just makes you wonder, if the vacuum itself is this complex physical thing, what other secrets might be hiding right there in the nothingness that's all around us?